Last DL, we started talking about modes in the context of thermal energy. A mode is basically just a box that we can put energy into. If we want to increase the energy of a substance, we have to put energy into all of its modes. We always have to put the same amount of energy into each mode on average. The more modes there are in a substance, the more energy we have to put in order to increase that substance's temperature. In this video, we're going to see how we can relate modes to a specific macroscopic property of the substance, namely heat capacity. Let's start by talking about what heat capacity is. Heat capacity is just a measure of how much energy we have to put into a substance in order to change its temperature by a certain amount. Heat capacity in general can be written like this. It's just the change in the thermal energy of a substance divided by its change in temperature. Before we relate this to modes, let's just take a moment to think about what this means. Suppose we have two substances and we're changing their temperature by the same amount, but one of them takes twice as much energy to do this. This means that delta E thermal for that substance is going to be twice as large as for the first substance, but delta T will be the same. So the heat capacity for that substance is twice as high. The higher the heat capacity, the more energy we have to add to the substance to raise its temperature. But how is this related to modes? Well, it's related to modes because in the last DL, we determined what thermal energy was in terms of modes. This is the expression we got to last time. The thermal energy in a substance is equal to the total number of modes in that substance times 1/2 times the Boltzmann constant times the temperature. If we want to determine what the change in thermal energy is, we just have to look at the changes in the quantities on the right-hand side of this equation. However, most of these are constant. The number of modes is not going to be changing unless the substance is undergoing a phase change. The Boltzmann constant is a constant, and 1/2 is, of course, a constant as well. So for change in thermal energy, the only difference is that we use a delta T here instead of a T. But if we've gotten here, we've almost made it to heat capacity. In order to find heat capacity, we just need to take the change in thermal energy and divide by delta T. Well, what happens if we divide this side of the equation by delta T? Well, the delta T's just cancel, and we're left with this. We now have a model for heat capacity. The heat capacity of a substance is just given by the number of modes that a substance has, times 1/2 times the Boltzmann constant. For substances with very large numbers of modes, the heat capacity will be large. And for substances with very small numbers of modes, the heat capacity will be much smaller. Again, thinking about what this means physically, you can imagine a mode as a box that we can put energy into. In order to raise the temperature by a certain amount, you have to put in a certain amount of energy into each box. If there are more boxes to fill, then you have to have more energy for the same change in temperature. Let's think about this number here, the number of modes. One thing that's very common is to write heat capacity for particular amounts of substances. One amount that's fairly common in chemistry is the mole. Molar heat capacity is just the heat capacity of 1 mole of a substance. So how can we write this out for a mole? Well, let's think for a moment about what the number of modes is. The number of modes is the total amount of modes for all of the particles in the substance. But we can just break this up into two pieces, the number of modes per particle and the number of particles. If we multiply those two numbers together, we'll get the total number of modes. So let's rewrite this for the case of 1 mole. In other words, when we have Avogadro's number of particles. This subscript here just means we're talking about the molar heat capacity of the substance. Notice something interesting. We have two constants multiplied together, Avogadro's number and the Boltzmann constant. This combination appears so often that we actually give it its own symbol. The symbol is R. You may have heard it called the ideal gas constant. We'll see why it's called the ideal gas constant a little bit later in the course. But this just means that we can rewrite this equation like this. We now have a model for the molar heat capacity of a substance. The only thing that it depends on is the number of moles per particle. Let's take a few moments to consider this number. We talked last class about how to determine the number of moles per particle for various substances. We said that for solids and liquids, the number of moles per particle was always 6. And for gases, we worked out a recipe for how we can determine the number of moles that each particle has. But it just so happens that there are some subtleties to this last part. So let's take a moment to consider them. Our model here says that if the number of moles per particle is a constant, then the heat capacity of the substance will be constant as well. 1/2 and R are themselves constants. But what if the number of moles per particle is not constant? It actually turns out that this is the case often in gases. This phenomena is known as the freezing out of modes. Let's go back to our analogy of modes as boxes in which we can put energy. The freezing out of a mode is sort of like locking one of the boxes. We can't add any energy to it, and so we don't. This may seem a little bit weird, but this is actually how substances behave. Below a certain temperature, particles in a substance are not allowed to rotate or vibrate. If you increase the temperature a little bit, they'll be allowed to rotate, but not allowed to vibrate. And if you increase it a little bit farther, the vibrational modes will become active as well. You can sort of think of this as unlocking the box and allowing us to put energy in. But why does this happen? That turns out to be an extremely interesting but also quite subtle question. The answer has to do with quantum mechanics. Now, we're not going to be studying quantum mechanics in this course, although you will see little pieces of it in 7C. Quantum mechanics just describes the way that very small objects behave. Quantum mechanics is not intuitive, but we know that it's right, or at least mostly so. This is indeed how particles behave. Below certain temperatures, some of their modes are not active. So let's think about what that would mean for this substance. If this number is changing, then the heat capacity is changing as well. In your DL manual, there's a nice illustration of this effect, which I'll show right here. Notice that for some of the substances, though not all, the heat capacity is increasing as the temperature increases. This is because the number of moles per particle is increasing as the temperature increases. Notice, however, that there is at least one or two substances where the heat capacity is not increasing with temperature. Let's think about why that might be. The case where this is most likely to show up is monatomic gases. A monatomic gas is just a gas that likes to exist as free atoms, as opposed to substances like oxygen, which like to bind together and form pairs of atoms. How many modes does a monatomic gas have? Well, we know that it has to have 3 kinetic energy modes, because there's always 3 kinetic energy modes per particle. And where are those 3 kinetic energy modes? Well, they're going to be the 3 translational modes, the modes that the particle has as it moves from place to place. But once we've done that, we're done. We've accounted for all the modes that the particle needs. There's only 3 of them. So the particle will have no rotational and no translational modes. But rotational and vibrational modes are the modes that are generally frozen out. So if a particle only has 3 modes, it's always going to have access to those three modes no matter what temperature you're at. And so if we increase its temperature, we would expect that its heat capacity would not change. Most gases at room temperature have all of their translational modes and all of their rotational modes active. However, vibrational modes may or may not be active, depending on what substance you're talking about. We do not expect you to know how many modes are active for every substance at a given temperature, but we do expect you to be able to use a graph of heat capacity to figure out how many modes are active. Doing this is relatively simple. For example, in the graph I just showed, the y-axis has units of heat capacity divided by the ideal gas constant. Well, we know that the molar heat capacity is equal to this. So if we divide by R, we're just left with this. So on the vertical axis of this graph, we just have this, 1/2 times the number of modes per particle. So for example, if on the y-axis we're at 3.5, then the number of modes per particle for that substance is 7. Keep in mind, this expression is only true for 1 mole of a substance. The constant R is equal to Avogadro's number times the Boltzmann constant. So obviously, this expression will not work if you don't have Avogadro's number of particles. However, if you look back earlier in this video, you'll see the expression we came up with that was very general. It involved the number of modes per particle and the number of particles. You can always plug in whatever number you need into the number of particles. If it fits with your situation, you'll get the right answer. But it's very common to be thinking about the number of moles of a substance when we're doing chemistry, not so much the number of particles themselves. So it's often very convenient to use this expression. Next DL, we're going to continue talking about heat capacity in the context of gases. Unlike solids and liquids, gases tend to undergo fairly significant changes when we add energy to them. Going forward, we're going to try to work out how these changes in gases come into play when we're dealing with heat capacity.